This lecture video introduces the sort of methods associated with modeling a quantum mechanical version of a hydrogen-like atom. So these atoms are hydrogen-like because they are single electron atom systems, right? So single electron. That means that what we are modeling is a nucleus. So we might say the nucleus is here, and the nucleus has a charge. It's going to be positive. So some number called capital Z, which is an integer, it tells us the number of protons present. And of course, the charge of a proton is positive E. So we'll say that the charge of the nucleus is Z times E, or some integer number of proton charges. And then, because it's a single electron atom system, here is the electron, and it is a negative charge, so the charge of the electron is negative E, and we'll just symbolize it as a little minus thing. And so, classically, we expect orbital style motion because these things are attracted to each other, and presumably it could go around in a cycling sense, like counterclockwise or clockwise. And this problem, right, needs to be three-dimensional because atoms are three space-dimensional systems. The electron can exist around the nucleus in three-dimensional space. So this is in contrast to Bohr, right? The Bohr model, the Bohr model of the hydrogen-like atoms was two-dimensional, which is not realistic, right? Atoms exist in 3D. The electron can exist around the nucleus in three-dimensional space. The Bohr model of the atom only did a two-dimensional modeling effort. Because if you think about it, right, this would be sort of something you might try first, because anytime you think of, say, the orbital motion of a satellite around a planet, like the moon around the Earth or the Earth around the sun, the truth is you can flatten that, right? The ellipse is a two-dimensional sort of object. It exists. You just have to find the plane in which the orbit is happening. But we don't want to, like you'll see that what we do actually is we start off by saying our atom can exist in three-dimensional space. So what we're going to do, oops, I forgot to erase this stuff here. So what we're going to do, right, is we're just going to follow the program. Remember, the program of quantum mechanics is to figure out how to understand what is the potential energy, right? And in particular, it's a function, right? And the potential energy function in three-dimensional space can be a function of x, y, and z coordinates, right? So once you figure out the potential energy function, which you already know how to understand, it's got to be the Coulombic one, right? So these two things are attractive, right? The electron is attracted to the nucleus, and the further separated they are, the larger the potential energy, and it's right. It goes with inverse the distance between them. But anyways, yeah, the potential energy function, and then after you write down the potential energy function, you write down Schrodinger's equation by filling in the potential energy function, and then you solve the differential equation, right? And the solution of the differential equation are the wave functions. And the wave functions, because our potential energy function is three-dimensional, our wave functions are going to be three-dimensional, right? So they're going to be functions of x, y, and z. Previous to this lecture, we've only been doing one-dimensional Schrodinger problems. So we've only ever had, say, psi of x. But now we're going to have psi of x, y, z. Okay, so the purpose of this video, honestly, is just to describe the potential energy function and then show you what Schrodinger's equation looks like. But what you're going to see me do is tell you that the problem is more natural in spherical polar coordinates, right? So instead of x, y, z, we're going to do r, theta, and phi, which I hope you have some experiences with. But Schrodinger's equation, it turns out, is solvable in a somewhat transparent way in spherical polar coordinates. In particular, it's separable in spherical polar coordinates. Schrodinger's equation for the hydrogen-like atoms is not separable in rectangular coordinates x, y, z, but it is separable in spherical polar coordinates, right? So let me put that word down. It's a separable differential equation in these coordinates, which is why people do it, because when you have a separable differential equation, that indicates a huge simplification in the math problem that you have to solve. Okay, so anyways, so let's start here with determining the potential energy function. So u of x, y, and z. So our nucleus is here. I'll just draw it as a plus. And then our single electron, let's say, is up here. And then I'm going to put down a coordinate system to look at this problem in. So let's say this direction here, which is sort of somewhat heading out of your screen. I'll call it the x. Here is another direction, also somewhat headed out of your screen, right? Can you see these arrows are kind of poking, like this y direction is poking towards the right, but somewhat out. And then the z direction is the leftover direction. It just points up. So here is the z direction. All right. So this thing right here, this electron, let me project to you its location above the xy plane. So I'm dropping what's referred to as an altitude. So if I drop the altitude, here is the location it's above inside of the xy plane, right? So the y coordinate is here, and the x coordinate is here, and the z coordinate, you have to be somewhat careful, because you have to follow the axes back, but the z coordinate is somewhere actually kind of high, right? You have to remember, yeah, it's kind of like you have to follow the diagonal. So above the xy plane here, you have to go up to the z-axis. The z coordinate's actually up in here somewhere. The z value is here, roughly. Okay, so anyways, so that's the location. But you know that the potential energy is actually really just a function of the separation distance. So the potential energy function is 1 over 4 pi epsilon naught, and it's going to be Ze, that's the charge of the nucleus, times the charge of the electron. So Ze times E, so that's Ze squared, and then it's divided by R. But this potential energy, we need to tack on, let me think a second. So if I draw this picture, right, this picture is positive for all values of R, but I know that the potential energy needs to increase with if the separation distance decreases. Sorry. So to get the correct behavior with this potential energy, we actually have to put a minus sign, like that. So this is our potential energy function right here. And r is the Pythagorean distance, which is just the square root of the sum of the squares of the rectangular coordinates, right? So this potential energy function, if you draw a picture of it, right, u as a function of r, what it does is as r increases, the potential energy also increases to a maximum value of 0. And for finite r values, right, somewhere over here, the potential energy, right, so the potential energy's actually got a negative value according to here, but you know that the potential energy, the important thing is how it changes, right? So the way that the potential energy changes is such that if you go to further out r, the potential is increasing, and that's what we know needs to be true for an attraction between two particles, right? The potential energy increases the further separated the two things are. All right? Okay, so here's our potential energy function in terms of just the distance between the two charges, or the electron and the nucleus. But in terms of rectangular coordinates, you just use the Pythagorean theorem. So that is the potential, right? So if I wanted to write down Schrodinger's equation now is going to look like this. Remember, it starts with, so let me write this. So Schrodinger now looks like the following thing. You go minus h bar squared over 2m, and then, so strangely, I'm going to write it this way. It's d squared by dx squared plus d squared by dy squared plus d squared by dz squared. These three operators operate on psi, which is a function of x, y, and z, right? And then you add the potential, but the potential has a minus sign, so it's going to come in with a subtraction. So it goes minus, and then 1 over 4 pi epsilon naught. And then I'm going to, let me erase the 1, I'll just, so I can keep things tight or efficient. So it goes z e squared, and then psi of x, y, and z divided by the square root of x squared plus y squared plus z squared, right? That's the potential energy multiplying the wave function, and this is equal to some constant that's identified as the energy, right, which is not a function of x, y, z. The energy is a value, some number of electron volts or joules, right, which is not a function of rectangular coordinate, but it multiplies our wave function psi of x, y, z, right? So this is the Schrodinger equation in rectangular coordinates, right? So I told you, though, earlier that it actually makes more sense because the problem becomes a separable differential equation, or a separable math problem, which is simple to solve, or simpler to solve, if you understand your problem in terms of spherical polar coordinates. So let me show you the spherical polar coordinates on this diagram here. So there is a spherical polar coordinate called r, which is simply the distance out to the location xyz from the origin. There is another coordinate, or part of the coordinate, called theta, and you read it as an angle where you start from the z-axis. So the z-axis is theta equals to 0, and then you go over to the vector that points you out to the coordinate. So that's called the polar angle. And then the other angle is called phi, and phi is read by looking in the xy plane. In the xy plane, you imagine going from the origin to the shadow of your coordinate, but in the xy plane, and you go from the positive x-axis. So from the positive x-axis, you wind around in the xy plane to look at sort of the shadow of your radius vector in the xy plane. So I've got theta, r, and phi in the coordinate system. So theta takes values from 0 to pi, right? So theta is the polar angle. You can only go from along the z-axis over to 90 degrees from the z-axis to 180 degrees from the z-axis. If you go beyond 180 degrees, that's the same as just going from the z-axis in the other direction. So theta is only meaningful from 0 to pi. Phi is meaningful from 0 up to 2 pi. So that this is called the azimuth. So the azimuthal angle. It's the angle in the xy plane, and you can imagine that you can go from the x-axis over to the y-axis, that's 90, back to the negative x-axis, that's 180, back to the negative y-axis, that's 270, all the way around to the positive x-axis again. So you get 360 degrees for the azimuth angle. And then r takes positive values from 0 out to infinity, right? So theta and phi are on these intervals, where theta is kind of the strangest one. It's only through 180 degrees. The azimuth goes all the way around 360 degrees. And theta and phi taken together can be considered a solid angle. And then r is the radial distance away from the origin. You could call theta the polar angle. So it turns out that z is special in this coordinatization. So z is not special in physics, it just is special in the coordinate system, right? You had to pick a polar angle. Okay, so that's kind of interesting. So anyways, so Schrodinger's equation in rectangular coordinates looks like this up here, and it's kind of simple, but and it turns out actually when you write down Schrodinger's equation in the spherical polar coordinates, it looks actually slightly more complicated, but it actually is simpler to solve the differential equation. So let me show you what the spherical polar coordinates version of Schrodinger's equation looks like. So I'm gonna do this in red. So the Schrodinger equation in spherical polar coordinates. Coordinates, yes. Okay, so what it looks like is this. So it goes minus h bar squared over 2m, right? So that is the same thing from Schrodinger's equation, but instead of, this is called the Laplacian. It's a derivative operator. So can you see that this thing is just raring to operate or act on some function? In the case of Schrodinger's equation, that function is called a wave function. But this operator is referred to as the Laplacian. And this operator, Laplacian, in rectangular coordinates, looks really clean. But the Laplacian operator in spherical polar coordinates looks actually kind of difficult and sort of strange, and you have to be really careful. So let me show you what it looks like. So I'm going to put a bracket, and it goes 1 over r squared, and then a derivative with respect to r. And then, though, what's really strange is you put an r squared and a derivative with respect to r. And then you follow that with a 1 over r squared sine of theta. And here is a derivative with respect to the polar angle, so d by d theta. And then it's the same thing. So you go sine of theta, d by d theta, like this. And then let me close that bracket. And then, so I'm not finished. The square bracket is still open, but the operator, I haven't finished writing down all the terms in the operator. So it goes plus 1 over r squared sine squared of theta, and then multiplying the operator d squared by d phi squared, like this. And then that's actually the whole Laplacian. And all of these things are going to act upon psi, where now we understand psi written in terms of r theta and phi. So we're not finished yet. This is only the kinetic energy term. And then we get minus ze squared over 4 pi epsilon naught 1 over r, times psi, which is a function of r theta and phi, and this is equal to E times psi of r theta phi. All right. Now, r theta and phi and x, y, and z are easily relatable to each other. So you can you can think about it geometrically, right? Like here is the relationship. You can think in terms of trigonometry and understand the relationship amongst the coordinates. But let me just remind you that the rectangular coordinate x is r times the sine of theta times the cosine of phi. The coordinate y is r times the sine of theta times the sine of phi. And then z, the polar coordinate, is just r times the cosine of theta, independent of phi, right? So this is the connection between the coordinates. But this right here is our math problem that Schrodinger's equation has given us. We have to solve this problem. So, and the technique is if you go into a differential equations class or a slightly more advanced quantum mechanics class, you use the separation of variables technique. To solve, right? So this is a mathematics technique of solving certain kinds of differential equations. Just to reiterate, this thing in red that I put a big box around, this thing you can solve with separation of variables. This thing up here in black, which is also the Schrodinger equation, there's nothing wrong with this equation other than it's not separable. You can't solve this by separating the variables x, y, and z from each other. And the reason is because x, y, and z are always intimately connected in R. That is, in a sense, R is more important than x, y, z by themselves. Or x, y, and z always have to come together in the form of the radial distance r, just honestly because of the symmetry of the problem. Our physics problem is spherically symmetric. The potential energy can't tell the difference between x, y, and z individually. There is no special direction selected. Yeah. Okay. So in the next video, I'm going to show you what the solutions to Schrodinger's equation look like. That is, I'm going to address the wave functions themselves. What we're going to see is that the wave function psi can be is going to come with actually three different quantum numbers. It's got the quantum number n, which is the energy level quantum number. It's got a quantum number L, which has something to do with angular momentum. And then there is a quantum number called m sub L. So these are the three quantum numbers. And they don't necessarily take integer values. But what they do is they specify the wave functions, the hydrogen atom-like wave functions. So that's what I'll describe in the next video.